Okay. Hello, everyone. Welcome back to CVT. Today we have with us Xinshuo, and Xinshuo is a PhD student at Robotics Institute of Carnegie Mellon University. She's supervised by Kris Kitani. She also received masters at CMU, where she worked with Yasir Sheikh and Kris Kitani. Prior to CMU, she worked at Oculus Research and as a research engineer, and her primary research interest lies in 3D computer vision and graph neural networks for autonomous systems such as self-driving cars. Specifically, her research spans the space of object detection, multi-object tracking, re-identification, trajectory forecasting, point cloud forecasting, collision avoidance, and congratulations, she was also awarded a Qualcomm Innovation Fellowship for 2020 and 2021. Today, we are going to discuss her work on improving autonomous driving pipeline using graph neural networks for object detection, tracking, and forecasting. We're glad to have you with us today. Please go ahead.
Thanks for the kind introduction. It's great to have a talk like one day after the holiday, because yesterday was Christmas days in North America. I'm not sure if there's such a holiday in India as actually, but yeah, it would be good to have a talk like in the middle of the holidays. Anyway, okay, so today I will be talking autonomous driving pipeline, like how do we improve it, specifically using graph neural networks. And I'll be talking about how we use graph neural network to improve like object detection, motivated tracking, and trajectory forecasting. Okay, go. Let's just get into okay, overview. So I will be first talking about the standard perception and prediction pipeline for autonomous driving. This is just to give you a overview, like for people who don't know the autonomous driving pipeline much. So then I will go into the details of how we use graph neural networks specifically for interaction modeling and in multi-object tracking tasks first. And then this is how I get started. And then I will just spread out to other domains like object detection and trajectory forecasting, how we extend graph neural network to those tasks as well. And then moving forward is one of the interesting things I'm working on recently about a novel pipeline, which is not investigated before. Like people have been like stick to the standard perception pipeline for many years. So there is a novel pipeline proposed, which is kind of interesting. So I would like to share today if there is time. Okay, great. So first, perception and prediction are important components in autonomous driving stack. This is kind of the commonly accepted like statement, especially for people in working in autonomous driving, either in industry or academia, because if we can understand what are around us and how they move in a short future, it will be very like useful to drive your own vehicle, the ego vehicle, like how to make the right decision in the following seconds, right? So here's the standard perception and prediction pipeline. So usually we have these modules. There could be other modules that are like in addition to these main components could be added to the pipeline, but the main things are here. First, we have the sensor data, and then these pass into a 3D object detection, give us some object detected, and then we track them through time, right? This 3D object detection is only performed at individual frames. And then once we track them across time, we have their identity. We can do trajectory forecasting by analyzing their motion pattern, so we can know where the object will move in the short future, and then we can make decision based on that. Okay, and then we usually classify the detection and tracking as the perception module and the forecasting and the prediction module. Okay, great. A little bit more details. So in terms of the sensor data, a lot of people in industry and academia working on like RGB for many years, right? This is the sensor we have worked for the longest time. And then recently, like recent several years, LiDAR becomes one of the other major components because they have very accurate 3D localization information, right? We can shoot the beam, the sensor beam, the LiDAR beam, and the returns based on the time of the light flights. We can calculate the distance of every individual point in the entire LiDAR point cloud. So that distance basically is a 3D like depth information, which usually is very hard to get from RGB camera images, right? Because you only get a list of pixels, whereas there's no 3D information inside it. Okay, and then there are some other sensor data which are kind of the minor thing, but people also exploring a lot, which I will not cover here. And then we do 3D object detection. Like I said before, this is usually done like at individual frames. We get 3D bounding boxes for each object. But sometimes people also do video object detection or video 3D object detection. That's kind of like a mixture of detection and tracking, but which is not kind of the main thing people use in autonomous driving stack. But it could be an alternative way of solving this autonomous driving problem. Okay. And then once we have these individual detected 3D bounding boxes, right, the 3D cube, and then we can associate them through time. This is mostly done by first like extracting some features for each object and some already established tracklets in the past. And then we can see how similar these past tracklets and current detection, like what kind of the similarity value they have, like pairwise, and then we can associate a new detection to the past tracklet and doing this like over again. This is kind of like the online multi-object tracking, right? So then we get the full trajectories after we receive all the frames. Okay, and the final step is unit trajectory forecasting. Because once we have the trajectories of each individual objects up to the current frame, we know how they drive. In the past, like say 1 or 2, 3 seconds, we can predict how they will drive in the next few seconds. Or it's not limited to cars, but also like pedestrians, cyclists. We usually care about all of these road participants when we do autonomous driving. Okay, great. So this is the standard pipeline. And what is the state of the art? Like there's a lot of progress in these domains, but like what kind of things people are working on recently? So I summarize some of them, but this is not the whole world because there's too much progress, which I cannot cover all of them here. But one of the big things is definitely like bigger models, better models from bigger data sets, right? So there are a lot of new data sets proposed in the last year. Actually, I should say this year because 2020 is not finished yet. So like in 2020, we have like Waymo's new things like they all published in this year, and we have the very old data set like Kitani, but they are pretty small in terms of the number of labeled instance and number of frames. But for the newer data sets, we usually have much more frames and much more labeled objects instance, which are very good for training large, especially 3D object detection model, which usually have like a large model that take a lot of memory and a lot of data. For the multi-object tracking and forecasting, usually it's like smaller because the level of structure is simpler. But recently, people also get into more complex models, right? Before then, like for tracking, people just use Kalman filter, which is not a deep learning based method, and it's very simple. I mean, in terms of these the complexity of the models. Okay, and the other line of improvements, this is more specific for trajectory forecasting, where like in the past, people all have these real data sets with a single ground truth future, right? Because in reality, although there are multiple possible futures that could happen, but in reality, there's only one future that actually happened, right? So this kind of one single future ground truth cannot help us understand all possible futures. So people try to figure out, okay, we know like the future is uncertain, there must be multiple possible futures that could happen. So why not like construct a data set with multimodal ground truth futures, right? So something like that could be very interesting. This will also help the evaluation of trajectory forecasting methods, because all of the trajectory forecasting methods, or most of them, like people are recently working on, are multimodal methods, meaning that they will predict like multiple possible futures given a single past trajectories, right? Because this is what we should do. Yeah, so in order to evaluate that better, we should have a data set with multimodal future ground truth specifically. Okay. So in terms of progress on detection, there's also a lot of them, but one of the most popular thing I would see here is the molecular 3D detection. This is kind of becomes popular in 2019, like one or two few papers that coming out, which really improves the performance if you can look at here, right? And then after that, there's really a lot of papers coming out because it seems like not of no hanging fruits are there. So people are much more eager than like doing this tech than before. And I also have one of the paper in this domain, which is kind of like the pseudo LiDAR based methods, and now becomes very popular, I think. And the LiDAR based 3D detection, this is another line of work where people use LiDAR point clouds. So the performance will be much more accurate, right? Like I said, because the LiDAR provides very accurate 3D depth information. And I guess the most recent popular trend is the sensor fusion based approach, right? Although in terms of performance, if you only use LiDAR point cloud, you can still get a very decent performance. But people are very like eager to know how, if we have multiple sensors, how we improve the performance, right? Because in reality, you cannot just rely on a single sensor because it can fail easily, right? For example, camera, it can have like over explorer. For LiDAR, if you have fog or rains, whatever, like this weathers, it will kind of break the sensor. So we definitely want to have multiple sensor fusion to get this method more robust. Okay. In terms of tracking, like for both 2D multi-object tracking and 3D multi-object tracking, there are a lot of progress over the common filter method that has been dominant in the entire literature for many, many years, like because it's very simple. But there are a lot more deep learning based methods that are coming out very recently. Okay, and then one of the trends in this area is that in the past we do this feature extraction from individual objects and then do data association to kind of compute the similarity and associate one to other, do this two-stage process independently or separately, right? So the recent trend is that to join optimize these two modules so that we have a one single network, or we can do one fast forward prediction of network. We can do like two things together instead of having two modules separately where you don't have the loss. Let's join optimize for the feature extraction as well, because the loss cannot be back propagated through the two things. Okay, great. And trajectory forecasting, again, there are a lot of progress. Like one thing that I want to mention is the goal condition forecasting, right? So when you want to predict where the object will move, like one important thing to know is what's the goal of this trajectory, or sorry, what the goal of this object is, right? If we know the goal, we have very different forecasts. For example, if you look at the feature, the picture in the middle, if the goal of the blue car is moving ahead, it's more likely that its trajectory is keep moving ahead, and the car behind it, the green one, also moves ahead, right? But if the goal of this blue car is to stop here, for example, if there's a red light in front of it at an intersection, then it should be stopping here. Like it's a very easy prediction, right? And then the car behind it will also stop. So it can make the prediction much easier if we know where the short-term goal of the object is. This is only limited to short-term goal because we don't know actually the long-term goal of each object is, right? Where the destination of the object. It's very hard to know that, but if we know that, that would be very good as well. And some other thing like leverage road context or road map, right? If we know like the road structure, basically where the road is and where the intersection is, it's much easier to make prediction without any context information like this, right? So this is one of the most popular trends as well in the industry. Like Uber, Waymo, they all kind of leverage this kind of information, I think. Yeah. Okay, and one last thing, which is also one thing that I'm advocating recently, but there are other people doing this track as well. Basically, they want to optimize the entire autonomous driving pipeline, the perception and prediction module, like join optimize these things together. So this will bring a lot of advantages, I think. So for example, if we train these things or optimize these modules separately, there will be definitely suboptimal performance, right? Because the 3D detection is not really optimized for the trajectory forecasting, the end goal, the goal that we really want to solve at the very end of the pipeline. And also there will be slow inference speed because we have to run these modules individually again and again and again. And there will be some redundant modules, or for example, feature extraction, right? We have feature extraction for detection, for tracking, and for trajectory forecasting. So some of them could be merged together. So if we do them individually, like multiple times, it could be very slow. So like some works are exploring joint optimization of these modules. Like one specific work is from Uber, the Rackhouse team. So they kind of propose to unify, to do the three things all together in a single neural network. So this is one of the things that definitely people in autonomous driving want to explore more in the future, because this will make the whole thing interpretable and also much easier than you run individual module again and again. Okay, great. I guess that summarized like some progress in this domain. There's more which I won't cover. But one thing that I want to particularly point out is that most of the work, even in these modern days, is that they are missing one important thing. So when they do this feature extraction or the feature representation, like most of the work, doing them independently for each object. So for example, if you want to extract features for like in multi-object tracking, you have 10 objects, you want to extract features for 10 of them. You just run, let's say, LSTM to every other, like every of the objects. Or if you want to extract image features, you just apply a reselect to each of the cropped images from like each of the objects bounding boxes, right? So that kind of independent feature extraction process is not so good, because you don't actually model how one object affect the other, or how similar they are, because everyone is going through a process independent of others. So how can we model such behavior or such things that one agent can affect the other throughout the entire neural network process during the feature representation learning, right? We know that one agent will definitely affect the others. For example, in trajectory forecasting, if we know this agent's trajectory is going left, and there's another agent moving together with this, for example, two people like working together and talking to each other, right? They're kind of in the same group. We know if one of agents moving to the left, there's the other agents that's going together with this agent should also turn left, right? Because they're in the same group, if we know such information. So many of the objects have some inherent like features or latent features that we can kind of model, and they are kind of similar or dissimilar to each other in different cases. So we should model such context information or such interactions between objects. So this is going to be the main topic of today's talk. Like, how do we encode such interactions throughout these modules? Okay, great. Yeah, I guess I finished the first part. Yeah, if there's any questions.
Right. There was a question in the chat box that why can't we use common object detection models like RCNN and YOLO for 3D object detection? Yeah,
we can. But I guess usually people use this for 3D object, and it's not really called 3D object. I mean, without any modification. That's usually called bird-eye view object detection, right? Because these fast RC and YOLO are basically 2D object detectors. So they are predicting a 2D bounding boxes. X, Y, WH, right? So you can apply that on the bird eye view, basically the top-down view. So the top-down view detection is also very useful in autonomous driving, because it gives you the depth information, but it will ignore the height information. So you don't know the height of the object is. So if there is a slope, right? Such information sometimes is important, because, for example, there is usually, I don't know what it's called in English, but sometimes when you have like multiple floors of the road, right? So if two objects are actually in the same spatial location, but at a different height, it will look weird from the top-down view, because two objects exactly overlapping with each other, but actually they're low because they don't have a same height. So such bird eye view detection cannot cover such thing. the 3D object detection I'm talking about here is representing the entire thing, the height, depth, and also the x-axis. So basically the entire 3D coordinates is measured in the 3D bounding box. So this is kind of contains much more information. But you can also adapt fast processing and YODO to do this 3D object detection as well. Basically, you will try to modify the phyllo head of the network by not just predicting x, y, w, h, but also L, which represents the length, and also height. And sometimes you also want orientation of the objects as well. So yeah, so you can definitely do that, but in some cases you are limited by some degree of freedom.
That answers it.
Yeah. Okay, great. So okay, let's go back to here. Any other questions? So that's kind of the set a stage for the background of the autonomous driving, I guess. It should be very straightforward, but if there's any question, I can take one.
No, it was very, very.
Is my connection bad, or is Shambhavi's connection bad?
I think it is Shambhavi's.
I think, yeah, Shambhavi's connection bad.
Maybe
Okay.
mine possibly. I see.
Yeah, I guess I can't hear anything. Okay, maybe, I don't know, should we wait her?
I think,
Yeah, I guess
continue.
both.
Yeah,
Oh, I guess she's lost.
yeah.
She'll get back. Yeah, some connection issues. I think we
Yeah.
can continue.
Okay, great. Okay, great. Yeah, so let's move to the first part where I want to introduce how we use graph networks specifically for interaction modeling, like I just said before. And this is going to be in the multi-object tracking task. And later on, I will extend it to other tasks as well. Okay, so first, let's try to understand what's the goal of this multi-object tracking task, or what's the issue of the current method, right? So remember, in the multi-object tracking task, the goal is to learn discriminated features, especially for different objects, right? So we have, the setting is something like this. We have a set of objects in the current frame, in the past frame or in frame t. And we also have a set of objects in frame t+1 or in the current frame, right? So in past frame and the current frame. And then we want to extract some features from this object. For example, like just one dimensional feature for each individual objects, right? So some vertical bar like this. And then we want to, since we want to know who matches to who or who belongs to who, like across these two sets, we want to get some similarity matrix, right? So this is 3x4 matrix where each value indicates how similar one object in the past corresponds to one object in the future or in the current frame, right? So since we have 3 objects in the past and 4 objects in the current frame, so the matrix is 3x4. Very simple. And then the bigger the value in the matrix is, meaning that these 2 objects is more similar than one of the object to the other, to a different objects, right? So for example, if this value is 0.8, it's very high, we know this third object in the past very much correspond to the first objects in the current frame. So we can associate these 2 objects like this purple one to this red one. So this is basically the setting of this multi-object tracking. So in order to do this task much easier, we want to learn discriminative features, meaning that for objects with different ID or different identities, we want their features to be very different to each other. But for objects with the same identity, for example, this purple one and this red one, we want their object features to be very similar to each other. So then we can measure this similarity value to be very high, right? So this is how it works in multi-object tracking and how we do this, how we solve this task. So what's the issue in prior work? So if you look at this network again, you will find that the feature extraction, like I said before, the feature extraction it is independent of each object, right? So if I have three objects here, we just run some, let's say, convolution neural networks or LSTM to get 3 features out of it. But then this is just an independent feature extraction process, right? So each one goes through the network independently of other. The other, and then the drawback of this is that there's no communication between objects, right? So in test time, basically each object feature doesn't know like what's the object feature of others. There's no information communicated through objects. So this means that we basically ignore the context information. And the other thing is that the feature is extracted from one modality. So usually people do 2D object tracking, use like 2D convolution neural networks. So this is basically 2D appearance feature. Sometimes people use the LSTM to extract 2D motion features. For people working on 3D multi-object tracking, like to get the entire 3D coordinate or 3D trajectories, they usually never 3D motion, right? Because they have the depth information. Or they use point net to extract some 3D appearance feature from the 3D point cloud of the objects. So there are very different modalities people can leverage, or very different evidence people can extract it from the objects. So it would be good to leverage all of them instead of just leverage information, like some information, right? Because all of these modalities could be complementary to each other. So this is also one issue, I think. So how can we address them? So first question is, shouldn't the feature depend on the other objects, right? The feature of every object depend on the others, right? So in order to achieve this, we kind of proposed a novel interaction modeling mechanism. So first we do the same thing like before, right? We have this independent feature extraction for each object. But after that, we want the object feature to be interactive to others. So we can learn some context information. So basically, this is try to learn some mixture of the features between objects, right? So although I didn't make any change to this vertical bar, like the corner or something, but there will be some updates or some modification to the features after this feature interaction. So I will introduce a little bit more later. And then if you look at this affinity matrix, so it becomes more discriminated and basically saying that the same objects identity have a higher similarity value. For example, it becomes 0.9 here, 0.998, where before you have 0.8. So this is how it works. So we want to get more like discriminative affinity matrix at the end of this feature interaction. And the other thing is that can we utilize all modalities, right? So this is very simple. So we basically want to use very different networks like 2D convolution neural networks, LSTM, 3D point cloud networks, all of these things to extract feature from each individual modality to get complementary information. Okay, so first, let's talk about the multimodal feature extraction. Like I said before, this part is very easy. So basically, like I said, I just use, in order to obtain this appearance and motion feature from the point cloud, I just use LSTM to get a 3D motion from the 3D bounding box trajectories and use point net to extract 3D appearance features. So these are very standard way of extracting features from the 3D trajectory, right? And the point cloud is basically cropped from the entire point cloud based on the 3D bounding boxes you have for each individual objects, right? For 2D, similar thing, we just use the 2D bounding box, which is projected from the 3D bounding box using camera projection, right? We have the camera matrix, by the way. So we just use the same LSTM, but here the input is 4-dimensional, not 7-dimensional. So we use CNN. Here is ResLab to extract the 2D image feature from the image cropped from the image patch, cropped from the entire image based on 2D bounding box as well. Okay, so once we have all of these 4 features, basically it's 4 1-dimensional features. I just concocted them together. So this is a very simple fusion, right? You just concatenate 4 features together to get a 1-dimensional feature at the end of the feature extraction process for each object. Okay, so that part is clear. Let's look at how the interaction modeling is achieved. with graph neural networks. So again, the goal is to learn more discriminative object features through interaction, right? So here is the steps. So first, we need to construct a graph, right? In order to do graphic convolutional neural networks or graph convolution, we need to have a graph. So the graph is basically nothing but a list of nodes and a list of edges between the nodes. So here we have two sets of objects, right? One set of objects in the past frame, one set of objects in the current frame. So we can just use each object as a node in the graph. And in terms of edges between nodes, we can just define some proximity, right? So for example, for each object, if there is another object within 5 meters, right? We just define an edge between them. So this is kind of very intuitive way of doing this, because when you want to associate one object in the past frame to one object in the current frame, you want to associate some objects that are close to each other, right? Because after one frame or across one frame, one object cannot just from the left of the world move to the right of the world. They cannot fly that fast, because usually we're dealing with pedestrian and vehicles. So one frame meaning 0.1 seconds. So the distance that they move in this one frame usually not that far. So in KT, we said 5, 10 meters, both are fine, like something like that. So based on that distance, it's basically a circle for each object. We can define which objects has the edge to the center of this object, right? So we do that for every object, so we can have this edge defined in a graph here. So pretty straightforward. And then once we have the nodes defined and edge defined, we can perform graph convolution for each node. So this, again, very intuitive. Basically, what we do here is that, let's say we have this one object feature, this NIT. T means edge frame T. I is the object index, right? And this is a multi-layer perceptron, this theta. So it's basically some linear projection that is learned through the network, through the training. And then this is basically the feature of this self object, this object itself. When we update every object's features, we will use its own feature as well, right? Because we don't want to forget what the feature of this object is in the past. And then we want to do some update. So this is what the update is. So basically, we look over its neighborhood, the neighborhood of this object. What's the neighborhood? It's basically what I said before. It's a list of nodes which has the edge connect to this object. So this is basically the NJT plus 1 here. So for example, if we look at the figure here, this NIT has 2 edges connected, right? So this NJT plus 1, and also there's maybe NJ plus 1, T plus 1, something like this. So we have these two orange nodes that are in the neighborhood of this blue node. So we just sum over them. And then the update we use here is basically a subtraction between 2 nodes. The node feature in the neighborhood and the feature of the self node, right? And the A here is, you can think of it as a weight, right? We don't want to update the feature of the self node with respect to the node in the neighborhood equally, because the node in the neighborhood can have different importance to the self node. So this is how, very similar to attention mechanism you've seen in none of these the modern techniques, right? So we basically add a weight matrix here to kind of put a different importance to the neighborhood node. And the theta 3 here is again a multi-layer perceptron, so we learn some linear projection. So this is how we update this node feature or graph convolution. If you think of the simplest way here, you can ignore this multi-layer perceptron. So this is end up with, for example, ignore this and ignore the weight matrix. Maybe you can just consider it as 1. So at the end of the day, it's basically at NIT plus NJT plus 1. minus NIT. So this is basically you transform the feature of NIT to NJ plus 1, right? Because these two NIT cross out, right? So if this NJT plus 1 is exactly the same, is exactly the object with the same identity in the next frame, you can think of it basically this transformation makes the NIT feature to be same as the NJT plus 1 feature, right? This is the thing we want to learn. Like I said before, we want to make the feature of the object that has the same identity close to each other. So by learning this kind of transformation from one feature to the other, this is how we achieve it, right? But obviously, this won't be the simplest case when we learn the network, because the multi-layer perception won't be just 1, 1, 1, 1, like all of the ones, right? And then the weight matrix is also not ones. So, but that's the simplest case you can think of how this transformation is doing. And once we have these load features, we can perform the edge regression. This is basically giving the affinity matrix we had at the end, the result we want to have. So how we do this? We just use, like, for two sets of loads, we just compute their distance by subtraction, and then going through some multi-layer perceptron, right? So for example, if two object feature is exactly the same, so this will become 0, right? And then we want to learn, like, the end of the value. This Aij is 1, right? Because these two object feature is exactly the same. We want their similarity to be 1. So in that sense, this multi-layer perceptron just need to learn the bias to be 1 in such case, right? Because these two already after subtraction is 0. But it won't be such simple case. Again, this multi-layer perceptron will learn some complex linear projection. But in the simplest case, basically means that this, if the feature of the two loads closer to each other, the final similarity value will be bigger. Yeah, so that's what we want to learn. Okay, some training loss. We do something very simple here, like the triple lane loss, right? We just, maybe it's not good to go through the mathematical details because it will take much longer time. But the intuition is very simple. We just want the feature with the same identity to be similar to each other, or the distance to be smaller, right? And we want the feature of the object node that have different identity to be larger, or the distance to be larger, right? The features of these two objects to be like very different, right? So that's what we want to learn, right? It's basically pushing the same object identity, the feature of the same object identity to be closer to each other, and the feature of different object identity to be further, as further as possible. So that's it. And the affinity matrix, the affinity loss is again very intuitive. If you look at this value, this matrix, basically in the ground truth, we simply just have like a single one at every column and every row, right? Because one object can only match to one object, right? Like there could be, it's impossible that one object in the past becomes a two object in the current frame, right? One, like, we cannot split the object, like one car becomes two car, right? So basically that means one object can only be matched to one object in the current frame, right? So that's how it works. So that means, go ahead. I guess. Yeah.
Yeah, but the number of nodes will keep on changing, right, between two consecutive frames, because the objects are getting added and some objects will be leaving from the frame. So the A matrix.
So yeah, that's a very good question. So at here in the graph, the number of layers or the index of layer is not the time index. So remember, I only deal with two frames, one frame in the past, one frame in the current frame. So it's not saying that after one layer, I'm dealing with the frame the frame after, and then after one layer, I'm dealing the frame after. No, that's not what I'm doing here. It's basically like convolutional neural networks, right? You can have multiple layers. So the data is the same. The object set is the same. I'm just processing the feature learning with multiple graph convolutional layers. Is that clear?
Got it. Yeah, got it.
Yeah. Yeah, so the number of nodes is remains the same in this case. But yes, you can do this spatial temporal graph neural networks as well. Basically, what I'm doing here is only spatial graph convolutional networks. You can think of that. There's no temporal update across layers. Okay. Yeah, so I guess I guess the affinity loss is not finished. Yeah, so basically we know in the ground truth affinity matrix where the 1 is and where the 0 is, right? The one only lies in where if two objects have the same identity, and the one, like there's only one, a single one in every row and a single one at every column. So we can just apply binary cross entropy loss to each individual item in the matrix, and also cross entropy loss at every individual row and column, because at every individual row and column there should be a one hot vector, right? Basically a single one and all others are zeros. So that should be pretty standard. Okay, and then some experiments. So maybe I will just skip these. Basically, we show that the multi-modal feature extraction is useful. Then, like, you extract a single model feature. So yeah, the more interesting thing is here. So is the feature interaction using graph neural network is useful? So let's draw some like figures again here. So we try different number of graph networks, graph layers, right? So if it's 0 there, means that there's no graph network at all, right? And then we add 1 layer, 2 layers, 3 layers. You can see the performance kind of goes up, like both two matrix. And then we can add more as well. But in this work, we kind of see that if we add more layers, the performance is getting into a plateau. There's no further improvement. But actually, in the work I'm currently doing, where we plan to submit to a journal, we show that if we add further layers, actually the performance can be further improved. But there need to be there are some tricks that need to be done in order to get it work. But at a very simple version, if like with 3 layers should be enough. If you add more, you probably cannot see the performance improvement further. So that's how it works in terms of performance. So the answer is yes. So we should let the object communicate with each other. So basically that will give us some context information and push the object feature closer if they have the same identity, and further if they have different identities. Okay, and some visualization, which maybe I guess maybe can make you understand this kind of easier. So this is how, like, what we predict in the network, this adjacency matrix or affinity matrix. So it's kind of like a matrix where in this case it's 3 by 3, meaning that we have 3 objects in the path, 3 objects in the current frame. So you can see the value, like in the first item, 0.9 or 899, this is very high. But in the second column and third column, you have 2 0.9 something. Both are very high. So this means that the network is a little bit confusing with the last 2 objects, like who I should match to who, right? Because this third row can be matched to the third column, or the third row can be matched to the third column, right? The value is pretty close, and it's hard to tell which should be matched to which. But after, if you put this matrix into the graph networks, and after some layers, you will observe the values changes. It becomes more clear who should be matched to who. So if you look at the matrix at the end of this prediction, like these 2 values get suppressed. It's from 0.9 something to 0.2 and to 0.4, right? So if I give you this matrix, it's much more clear. You should match the third row to the second column, right? And the second row to the third column, right? Because that's the biggest values, right? So this is how this graph network works. So it kind of suppresses the value that in the matrix, where the object have different identity should have lower similarity values. So this is pretty close to the ground truth that we have for this frame. where you can see the ground truth is just 1010 something. Okay, so I guess sorry. So I guess this kind of example can is very easy to understand. So this is how the graph network evolves the adjacency matrix or evolves the node features, which then affect the adjacency matrix at every individual layer. And some results, which is pretty standard. Okay. Yeah, so we've introduced this, how use graph network for interaction modeling in tracking. Let's then how to talk about how to extend this to detection and forecasting. So once we understand these, the main component, is very easy to extend actually. So first, let's look at the detection. This should be pretty easy after if you understand the part that I just introduced. So I will just skip that. Yeah, so this is how it works. So since we already have a method for multi-object tracking with interaction modeling, right, with the graph networks. So this is basically this part, right? We have feature extraction from past and feature extraction in the current frame, and the GN for feature interaction, and the multi-object tracking head, which I just introduced, the age regression, if you remember, right? Which gives you the affinity matrix. So how do we extend this to detection? Very simple. If you look at this part, I'm highlighting here. If I also wanted to do detection, meaning that we don't have a provided detection in advance, but we can have some anchors, right? Like fast RCN, right? We define some anchors in the current frame, and we want to classify which anchor is the actual true objects. So I just replace the provided detections in the current frame with like several hundred or several thousands of anchors. Anchor box. This is very simple, right? And the feature extraction is the same. It's just the kind of the thing we need to do here becomes more heavy because we have could have thousands of anchors, right? The feature extraction takes more memory. But that's it. So this part is very simple. And then also we just need to add an object detection head using the same feature we had after interaction modeling. So remember, after interaction modeling, every node feature is updated, right? And the age feature is also updated, and the age feature is used in edge regression, right? But the node feature we can use as well, right? The node feature for each individual anchor, we can use it to do classification and regression, right? So this is basically some one-dimensional feature for each node. We just ran through a multilinear perceptron to regress it to its delta of the XYWH in order to learn a more accurate bounding box location, right? Because the anchor is usually not accurate enough, right? We want to do some regression. And then if we have multiple class, like humans, cars, cyclists, we need to do classification as well. So this just saying that this object detection head is nothing but some multilinear perceptron, which is operated on the y-dimensional feature of the node, where it's representing each individual anchor, right? So if we want to do 2D object detection, we just regress 4 values, delta X, delta Y, or delta Y, delta W, delta H. If we want to do 3D object detection, this could be more, right? Delta length, delta depth, delta whatever. So that's it, very standard, right? And then this kind of very simple approach gives us very high performance in the multi-object tracking challenge. So in this case, we are doing 2D object detection and 2D multi-object tracking jointly, but it can be easily converted to 3D as well. So we get the highest performance in MOT15 and MOT20, and very decent in 16 and 17. So even with a simple approach that I just introduced. Okay, and also a lot of videos. Yeah, maybe I just can skip these. It's just give you some very nice and decent results you can find online on the leaderboard as well. Yeah, I guess it's more interesting to show some analysis, like if we disable the graph networks, how will it change, right? So this is more like an ablation study, right? So if you compare this top and bottom row, so the bolded bounding box is something good. It means that we can detect this object in this frame, in this method, but cannot detect in the other frame. So basically, if you see bolded bounding box, mean that this is performing better than the other. So basically, saying that the top video, you can see more bolded bounding boxes in the bottom one, saying that the top video has less false negatives, and the bottom one has more false negatives. Yeah, this is the same. I'll skip this. And also there is, this is a fair multi, which is a very famous method in multi-way tracking right now. So if we compare our method with them, we can also see more bolded bounding boxes in our method. Yeah, and also I guess this work presented before in CV talks. This is from Nora's team.
Right.
The neural solver for multi-way tracking. So this one is really very similar to the work I just presented. Basically, both use graph neural networks, but the main difference is that they only do graph neural networks for tracking, but the work I'm showing here is doing graph neural network for joint detection and tracking, and there will be some difference in the network architecture. And you can see from the results, in the top, we have more bolded bounding boxes than the bottom. This is saying that our method has less false negatives. So that's why the numbers becomes higher in the leaderboard. So yeah, I guess if you look at all of the leaderboards, our numbers is higher than this work. The idea is pretty similar. It's just our method is more tricks, I think, like more joint optimization, so that the performance can be higher. But it's both needs saying that using graph neural networks is helpful to improve multi-object tracking and also object detection as well. Yeah, and more comparison. This also compared to the neural server.
So I think second paper is presented in computer vision talks already.
Yeah.
Learning a neural solver.
Yeah, exactly. So yeah. So I think that's the main thing. And the other thing is to extend these graph neural networks for trajectory forecasting. So again, this will be very simple, like I just said, how we extend it to object detection. So we just add an additional branch. So maybe not this thing. Yeah, maybe it's important to highlight this. So this is the standard pipeline in prior work where you do tracking first, and then once you have the tracking result, the trajectories, you do prediction, right? You do trajectory forecasting. So there are several disadvantages of this pipeline. So first, again, there's no interaction modeling. Second, because you have these two modules separate, you don't have this joint optimization, which will lead to suboptimal performance. And third, again, it's the slow inference because you have redundant feature extraction module in two things. And the final is the error propagation. Basically, if you do these two things in sequential order, if you made an error in tracking, you will propagate this error to forecasting, right? So this is so-called error propagation issue. So in our work, so we basically parallelize these two things. So tracking and forecasting is done jointly and in parallel. So this is to mitigate the issue that I just said. So first, we share the feature learning process. This will lead to faster inference because we basically throw the redundant modules, and we didn't see actually any performance like it's hurt by this. Basically saying that the feature learning can be shared for these two tasks. And the second, we use graph networks again for interaction modeling in the middle. This is similar to what I just said for detection as well, right? And third, we just add a trajectory forecasting model, right? This is standard, just a VAE for each object and the sample trajectory out of it. So this is to alleviate error propagation because tracking and forecasting is done in parallel. And finally, end-to-end training, for example, very easy to understand. So we don't need to train two things separately so that the joint optimization can be possible, which improve the performance. So again, we show some experiments which basically saying that if you add join optimization, the performance is improved. Pretty clear. I will just skip this part. Again, if we add multi-object tracking to the pipeline, the forecasting performance can be improved. And vice versa, if we add forecasting to the pipeline, the tracking can be improved. So basically saying that the two things are complementary to each other. If we do them jointly, the performance we achieve is the best. Yeah. The more interesting thing is here, which relates to the topic of this talk, right? So the interaction modeling, how is that useful, right? So if you look at this two figure, because right now we have two tasks, right? Tracking and forecasting. So if we add graph neural networks, especially at the number of two layers in this case, the performance for both branches achieve the highest numbers. For trajectory forecasting is measured in error, so it's lowest, the lower the better. But for tracking, it's the higher the better. Yeah. And some performance, some quantitative results again, which illustrate our network can do tracking and forecasting simultaneously, right? The color coded bounding box represent the tracking result, and the trajectory, the predicted trajectory on the ground represent the trajectory forecasting results. So usually work in the like prior work only do two things separately, so they only have one of the results, but we have two results simultaneously here. Yeah. So I guess that's it. I don't want to really I don't want to cover the last part. So yeah, if there is any question so far, I can take. So that basically the main part of the talk. So we kind of cover the standard pipeline for perception and prediction, and we introduced the graph neural network, how it works for tracking by introducing the interaction modeling to the graph feature representation learning process. And also how we extend this interaction modeling to other modules like detection, trajectory forecasting, right? It's pretty simple, but just adding additional branch and shared feature representation learning and adding some noise. So that's it, I think. And we can get very decent results in all of the ablation. So I guess that's it for the talk today. If there's any question, we can start here.
So this was actually interesting, like using GNNs for interactive modeling. So
yeah.
I mean, it got me interested in the GNN field. Also, I had a doubt about your paper, like the results seem pretty interesting, but are there any limitations of your work? Like, is there something which can be improved or something like that?
Yeah, there are a lot of limitations. So first, like I said before, the graph neural network has some limits itself. So if we add more layers naively, the performance won't like be further improved. So this is why this is a problem called over smoothing or overfitting. So basically saying that if you add more layers, if you look at like affinity matrix that were predicted, at the end of the day, all of the values in the affinity matrix will become the same. All of the values. So why does it happen? It's very simple to imagine actually. So basically what the graph convolutional neural network is doing is basically to mix the feature between nodes, right? Like I said before, it's basically obtaining a mixture of features. If you mix them too much, at the end of the day, you basically get everything the same, right? You are same as me, and you are same as other, and everyone's same as other. So you get a affinity matrix, let's say with all values equals to 0.5 or 0.6. Then how can you use that matrix to do data association to match to who, and like you don't know who should be matched to who, right? So that's one issue that's called over smoothing. So there are some techniques can be addressed that. So we're exploring that thing. And also the other thing that's mentioned by Nikhil, the spatial temporal thing that we didn't consider yet. So if we have more, so right now we only dealing with 2 frames, right? 1 frame in the past and 1 frame in the current. If we have more frames, how can we do joint data association, let's say across 10 frames together? And then we can have a bigger graph. Like one graph only take care maybe spatial, and the other graph take care the temporal. Now across temporal thing, we have different number of nodes because some object can leave the same and some new object can come in. So how should we like model such a bigger graph and learn a better feature if we have like more frames of information? So that's also a limitation that we don't have that capacity yet. Yeah, and there are more, but I guess yeah, that should be enough.
Yeah, that answers the question. Also, I wanted to know like what exactly is the data association model doing? Like how it is different from the interaction. So
You mean data association?
yeah,
How it's different from GN interaction modeling?
yeah.
So usually when we say data association, we mean the last step. So once we have this affinity matrix,
Mm-hmm.
how we get the final match, right? The final decision, like which object should be matched to who. So in that, to do that, we use Hungarian algorithm. So in the sense that our graph network for interaction modeling, it's just to output a better affinity matrix output. But from the affinity matrix output to the final match, we use Hungarian algorithm, the standard algorithm, to solve the match. It's more than an integer programming thing. So so that part is different from the graph network interaction modeling, where it's just to learn better features, right? It's not solving the integer programming problem.
Right.
Yeah.
Can I go ahead with a general question, not much related to the paper, but a research-based question?
Yeah, of course.
Yeah, sure. So, like, since your master's and PhD happen in the same school, was the research interest also same?
No, no, very different. So
Okay.
I think during master, I was working on like human analysis, more like, for example, hand gesture understanding, face key point understanding, and human skeleton recognition, like human pose estimation, something like that. So it's more like how we understand the detailed human motion, like even for like your finger, how should they move? So such detailed or fine-grained motion, instead of the motion that I'm caring about right now, which is like the vehicle or basically the trajectory of human. So this is more like coarse motion understanding, right? We just want to know where the human is moving instead of how they move, like does their hand moving through the process or how our facial expression is changing, so such things. So yeah, so there will be some shift because my advisor is changed as well, right? So that's probably one reason, but also my own research interest has evolved.
Right. So another question that would follow this one is that, like, since most of us here are undergraduate students, and I was also previously working in human pose estimation and human pose recognition, but now I'm shifting more towards biomedical imaging. So when should one actually settle down with one research area, or like, because we are undergraduate students, we just find too many things interesting and we are just jumping on from one place to another? And should we go for the area which has lesser competitive going on thing, or should we go for an area that just interests us the most, even if it is very competitive?
Well, that's a very hard question. There is no answer to your life, to everyone's life, right? So I would say when you go to a PhD and do 1 or 2 years, then it's pretty hard to change your research interest after, maybe. Because you have to, like, when you want to defend your thesis or you want to start your thesis, you have to have a goal in your mind, right? So when you write your thesis, there must be a topic or story you are selling, and everything added to your thesis should be support that main story, support the goal you want to solve. It should not be scattered. Like here you do some work in human pose estimation, and there you do some work in biomedical, like bioimaging process or something, and then here you do something in, I don't know, like whatever thing. You can't unify them in a single coherent story, then you can't, you don't know how to write your thesis. There's no way to write it actually. So then you can't graduate, obviously. So then after you do PhD for a while, then you have to start to just stick to the thing you want to work on. But I would say before that point, you can try anything you are interested. That's fine. For example, when you're undergrad, you do this, and then when you're a master, you do something else. And when you start a PhD like first year, you can try something random as well. You may switch advisor, you may switch university, right? And then you may switch your own research interest, or maybe your research interest is actually limited by your advisor. For example, you have a funded project, right? So when you do some master students, you are funded by some projects, and this project is asking you to do this. So you cannot do something else. You have to do this. Even though your research interest is lies in somewhere else, but you can't do that because this is where your funding is coming from. So you have to do this project. So then it's kind of like shifting your research experience like externally, like forced by something else. It's not forced by your research interest. But anyway, so that means like throughout undergrad, master, and earning of your PhD, you might change a lot. I guess that's fine, as long as you stick to something after you really dive into your PhD and you kind of consider your thesis and what you really want to solve after you have exposed to different kind of areas, right? But after your PhD, maybe you get into a faculty position. I don't know. I'm not a faculty yet, so I don't know. But I've seen many, like for example, my advisors, they shifted their research interest as well, right? So after they become a faculty, they kind of broaden their research interest and do many things else, like do many things they didn't do in their PhDs, right? So you can be like doing more broader and broader research as long as you are interested. But during your PhD, it's more like just stick to one thing and support everything to it.
So there are two questions. Like, thank you so much for your answer. We like guidance is one thing we really need at the moment because we stand at a very uncertain situation.
Yeah.
There are two questions related to your work in the chat section. I'll read them out. In GSDT, edges are defined across frames that assures object-object relation in temporal domain. But how do we assure that in spatial domain?
Yeah.
There was a brief description in the paper regarding that, but I had some difficulty in understanding.
Okay, yeah, sorry for the confusion. Maybe we should update the paper.
Actually, it is mentioned in the paper that so this is actually true. Like it has, it captures the temporal relationships, but only for first GNN layer. Like for the second GNN layer, it will communicate with further nodes. So the nodes which are not directly connected with the nodes, and therefore you can have the spatial relationship too. So basically, a node in the single frame with can communicate with other node in the same frame itself. So
yeah. I think I understand. So basically, there are two things that you can try differently. One thing is that you don't limit the object-object relationship across frames. You can just add even the edges within frames. You can do that, right? Just basically define a different set of edges, but that's not what we do in the paper, I think. But that's kind of the easy way to solve the problem, solve the question. I guess I don't know who asked, but basically that's in that way you can just have the both spatial and temporal correlations or relation modeling at the first layer, right? But the thing we read in the paper actually means that in the first layer or in every layer, if we only have the edges defined across frames, right? So that means the message passing is only done between, like, across frames. So in the first layer, there's no way you can change the load feature within frame, right? So for example, if you have two load feature in path frame, they won't communicate with each other in the first layer for sure, right? Because the load feature in path frame only communicate with the load feature in the current frame. but the thing we are explaining in the paper is that if you have more layers, let's say if you have an object in the here and an object in here, in the first layer you communicate them to each other, right? And in the second layer, this object could be communicated to a different nodes in the path frame. So this is how it moves, right? From left to right and from right to left. So when you have multiple layers, things can go like further. It's not like one hoop relation modeling. You can get multi-hoop relation modeling. So meaning that the mixture of the feature, the load feature, can be propagated to a further range, right? So you can be propagated from the last frame to the current frame and propagated back to the current frame, to the past frame. So that is what we explain in the paper. So you can get this spatial, you can mix the load feature in the single frame, basically the spatial domain, by having two layers, right? The load feature in the past frame can be propagated to current frame and propagated back to a different node. So this is how the spatial relation modeling is done if you have more like layers with only edges across frames. So that is also possible. Yeah.
Right. Answers the question. Another one is by Dikshita. She asks that how was the performance and limitation of the model when multiple types of objects like cars and pedestrians were present? Like instead of solving the regression problem, you have to solve the classification problem.
Yeah, I think URNA is fine. The performance will not change a lot, except for detection. I think detection, especially 3D detection, sometimes is affected a lot because in many of the 3D detection approaches, people define some default size for each object, right? And then when they regress the object size, basically the 3D bounding boxes, they regress a delta based on their default size. And the default size for different objects like car, pedestrian, and cyclist can be very, very different, right? The car is 4 meters long, and the pedestrian is like 0.5 meters long. In terms of length, I mean, height's probably close, but then the width is also very different, right? So the default size could be very different. So if you do 3D object detection, like many methods are doing them for each individual class. So basically, if you want to have a detector for every class, you just train them separately multiple times. You train a detector for car, you train a detector for pedestrian, you train a detector for cyclist. So this is usually what people do in 3D object detection. But in 2D object detection, where the size could be very much similar across objects, because right after perspective projection, the size could be very different. So then people can just do multi-class classification altogether for all objects. I don't think there's much like drawback of doing that. But for 3D, yeah, it's the story is kind of different because there is no projection, right? Then the car has the same size all the time, right? The 4 meters long all the time. But if you do projection, it could be the size could be very different. Like further range, the car could be very small, and when the car goes to very close to the camera, it can be very big. So then across different object types, the size could be similar because there's no really the kind of the default size for each object. For tracking, it's fine, I guess. If you do multi-class tracking, usually it's fine. For trajectory forecasting, I think it's fine, but people usually do them separately for each object as well, because they think, for example, pedestrians, the motion pattern is very different from vehicle motion pattern, right? Because the speed, the velocity is different, right? And the route is different. Like the vehicle is more like a like very stupid, always moving straight. Sometimes turn left, turn right. It's more like a robot because it's a rigid vehicle, right? And then for humans, it can like it's very hard to predict. You can walk everywhere, you don't know. Especially like in some camp, like there are a lot of data sets that's recorded in campus, right? It's not on the road where people just also follow the road. In campus, they can just walk everywhere, you don't know. yeah, I guess that answers the question. So
Yes,
yeah,
that answers the question perfectly. And I guess we don't have any more questions. Yes. It was great hosting you, and thank you for the introduction you gave to the problem statement. That was really helpful because not everyone is usually working in the same domain. So the introduction helped a lot, the starting part. It's great.
thank you, thank you. And also,
Again,
yeah,
yeah,
it's nice to talk here. Thanks for the invitation.
we are glad to host you. We're glad to host you. And we look forward to so much interesting work from you in the future. We'll be following you.
Thank you.
Thank you, Xinshuo, for taking time and giving a detailed presentation.
Yeah,
The slides
thanks.
are very detailed and very helpful.
Yeah.